Good morning, good afternoon, or good evening, wherever you are located, and welcome along to the AMETEK Solid-State Controls Understanding SCI Schematics webinar. Thank you for taking your time out of your day to join us. Your time is precious, we understand that, and we appreciate you coming along. If you don't mind, if you can type in the chat bar that you can hear me while we are waiting for everybody to join, that would be appreciated. So while we wait on everybody getting on board, if you can just type in the chat bar, say you can hear me loud and clear, that would be excellent. Good stuff. Thank you very much. So once again, while we wait for everybody, we'll go over a few things regarding the webinar. First of all, my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls. I am located in the Stafford office in Houston, Texas. As you can tell from my accent, I'm not from Houston originally. I was from Scotland originally. I worked in the North Sea, working on UPSs for just over 10 years. And then I moved to the USA about 10 years ago to continue working on UPS systems. So therefore, I have over 20 years in the industrial UPS industry, and I've worked with all major UPS charger manufacturers. It was only up until 5 years ago actually, that I joined AMETEK SCI and worked specifically with AMETEK. Regarding the webinar, there's going to be a lag of around about 30 seconds between you hearing my voice and me seeing a question. And that was a good example of when I asked if you could hear me. It took about 15 to 30 seconds for me to see the replies. Webinar Jam is the platform that we use. And, you know, obviously, you can watch this on your phone, you can watch this on your laptop, or you can watch this on an iOS device. So Webinar Jam has to decode and send all that information out, and in doing that there is about a 15 to 30 second delay on that. So please bear with me. If I don't see your question immediately after I've said something, then that is why. And in truth, we do try and keep the questions to the end, so you can type your questions in the chat bar at any time, but I will try and leave them until the end to answer all the questions in the Q&A session. Webinar Jam has a panic button on my side, so if I start to see people saying that you can't hear me or that it's frozen, first of all, the first thing that you should do is try and refresh your browser. If that doesn't work, let me know, and then I may have to press the panic button, and that starts a whole new room and invites everybody back into that room. Never had to use it yet, so but in tests it seemed to work well. The other question that we get asked a lot is, will the webinar be recorded? And yes, the webinar is recorded. You will receive a link from the same email that you received your invite to, and you can go and watch the webinar back again. I think it's about an hour after the webinar is complete. But the thing about the Webinar Jam recording is you have to watch it as a whole webinar again in its entirety. You can't fast forward it. You can't go to specific parts. So it's not really conducive to going to specific parts and recapping what we've gone over today. What our fantastic marketing department do is they take that video, they convert it to an MP4, and then they upload it to the AMETEK Solid-State Controls YouTube channel. And that way you have complete access to the video, fast forward, pause, rewind, do whatever you want to do when you're watching it back. And as always, the webinar should last about 1 hour, and that completely depends on how much I talk, which can be a little bit too much sometimes, and also how many questions we get asked at the end. Okay. So Today, we're going to try and help you understand the most common symbols used in an AMETEK SCI schematic, understand the flow of an AMETEK SCI schematic, where the power flows, understand the role of semiconductors and how they play a part in the power conversion, understand the power flow through the schematic, discuss the role each control board plays in the system, and discuss how alarms monitor the system. Okay. So that is what we're trying to get out of today's webinar. So the first set of drawings that we're going to look at is for what we call the microfarrow UPS, or the SE UPS. And this is the UPS that has a ferroresonant transformer. And some consider it the legacy UPSs that we make. So they are digital, they are controlled by a processor, but the regulation on the output is done by a ferroresonant transformer. And this is the first page of the drawing package. So really, this is the overview of your whole system. And you can see on the left-hand side here, you can see that this is the general arrangement of the UPS. At the top here, this is the top view looking down, and you can see that the door on this system opens from the left. You can see here, this is this one here is the front of the system. Excuse my terrible circle there. This is from the side, and this one here is looking up from the bottom. Okay, and it's got all of our dimensions, and it lists all the breakers and all the good stuff that you need to know about the physical size and what all the meters and breakers are on that panel. At the top here, we've got a block diagram, which we'll go into. We've got our startup procedure, and also the front panel indications. So we tell you what each meter is, what it's labeled as, and what it does. And we'll go into these in depth over the next few slides. So first things first is the bottom right-hand corner of that drawing. And that tells us how many pages there are in that particular package. So it's saying sheet 1 of 2. Okay, this is the outline for a 10 kVA microfarrow SE UPS. This is a very important number. If you ever contact the after-sales service department here at AMETEK Solidstate Controls, we are always going to ask you for the serial number. And the serial number is also called the project number on the drawings. And that is how we reference everything in our computer system. If we're looking for the drawings internally, or if we're creating a work order, or if we're doing anything regarding a UPS, we need to have the serial number, because it will tell us exactly what system we're dealing with, what the options are. It gives us all the information that we need. So that is the important thing about that bottom right-hand corner. Okay. And then on the left here, you can see the labels on this particular UPS. And remember, all of our UPSs are customized. So each UPS will have different meters. But let's take this one, for example, V301. If we look over here at the table, V301, that is the DC output voltmeter. Okay. And A1, if we look up here, A1 is measuring the AC output, and it's an AC ammeter. Okay, so that gives you a description of what the meters are. And then you can see in this section here, our breakers are labeled. So B301, that's this one here, that is the AC input, and it is a circuit breaker. So quite self-explanatory. And then what I've done is I've blown up the block diagram that's on that first page. And this gives you some really good information that's in a non-schematic form. We don't go into too much detail, but it has all the information that you need. So on the left-hand side here, we have the AC input, and on this system, it's 480 volts in, 3-phase, 60 hertz. And you'll probably notice one thing here. We are not running a neutral to this UPS. And when we get to the schematics, I'll explain that in a little bit more detail. So this line here, that delineates the outside of the UPS. So as soon as we go to the right-hand side of these terminals here, we are now inside the UPS. And terminals 301, 302, and 303, that's where you connect your AC input, your 3-phase cables. Then that goes through B301, which is our AC input breaker. That goes into our rectifier battery charger, which converts AC into DC. Okay. And then on the output there, we have V301, which is a voltmeter, and A301, which is a DC ammeter. So we can tell whether the battery is charging, discharging, how much current is flowing on the DC bus, and what the voltage of that DC bus is. And they are analog meters on this system. And then you can see here that we then parallel off to the battery, and we have a battery input breaker, which is labeled B1. Okay, and once again, at the top here, it tells you what our expectations are. And our expectations are that the battery can be between 105 and 140 volts DC on this system. So we know that it is a 60 cell, probably a VRLA or a VLA, a vented lead acid battery. And it's saying that nominally, if we had full load on this 10 kVA system, we would expect 98 amps. Okay. But we're saying that it can go up to 112 amps if we are discharging the battery and we go down to the final voltage level of 105 volts DC. So when you need to rate your cables, you have to keep that 112 in mind. So you have to size your cables outside this system to be able to carry 112 amps. Okay. Also, like I said, the battery is in parallel with the DC bus, and therefore the output of the rectifier charger and the battery are connected directly to the input of the inverter. And the inverter takes the DC and converts it into AC. So out here we have AC, and we have V1, which is a voltmeter on the output, and we have E1, which is a frequency meter on the output. Once again, both analog meters. And then we go into the static switch. Now, whenever I go through any presentation on UPSs, people always get confused with the static switch and what we call the RMBS, which is the remote manual bypass switch. And the way that I try and get you to remember it is static switch. Remember static. Static means there are no moving parts. Okay, it's not static electricity. It's static as in there are no moving parts. Okay, so the static switch is an electronic switch that chooses between inverter operation and bypass operation automatically. Now, the UPS is programmed to choose the inverter at all times, unless something happens to the inverter output. And then if something happens to the inverter output, then the system will transfer over to bypass automatically, and the bypass will supply the load circuits here, because our loads are out here on cable 199 and 15. Okay, now, yes, a lot of people are going to say, well, wait a minute, this is drawn as a switch. In truth, I don't know why we do that, and I don't think it's the best thing to do. It can be drawn much better than this using the actual symbol for a static switch, which is back-to-back SCRs, but we choose to draw it as a switch. So don't get confused. This is not a mechanical switch, although it looks like it. This is a static switch. Okay. And then on the output of the static switch, going out to our loads, we have an ammeter. showing how much current is flowing out into the load circuits. So in normal operation, power flows like this out to your loads, and then we also keep the batteries trickle charged. Bypass supply is on. Okay, and we'll mention this in just a moment. The bypass supply has to be the same voltage as the AC output. So as you can see here, it's 120 volts, single phase, 60 hertz, because our output is 120 volts, single phase, 60 hertz. Okay, and the bypass has to be able to supply the same current as the output, because if the inverter fails, okay, we are expecting the bypass supply to then feed power out to the load circuit. So if you had full load of 83.3 amps out of the inverter, then we have to be able to supply that from the bypass. So when sizing your cables out to your load circuits, we know that 83.3 amps is what we would expect at full load, and the bypass is going to have to supply that as well. So size your cables correctly for both of those amperages. And then we'll discuss this output bus arrangement later on when we go down to the schematics. The only thing I didn't mention here was we also have a bypass source AC input breaker. So that is a way we can disconnect the bypass source if we have to. So that is a breaker on the front of the system. So there's 3 breakers on the front of the system: B301, B1, and B4. B301, this one here, is for the AC input. B1 is for the battery input. And this one here is the bypass source AC input. Some people call it the dirty power or the alternate source. They're all 3 terms are interchangeable. Okay. The next page of the outline drawings is the customer connections, which is here, and the mimic panel, which is here, and then the alarm connections, which is here. And we're going to go into each of these in detail. So this is the customer connections in specifically this microfarad UPS. Okay, and as you can see, the cables that we mentioned before for the 3-phase input, 301, 302, and 303, that's the cables there. So you would need to connect your cables from your MCC, so A phase, B phase, and C phase, into here. Now, we do give you 2 lugs, so you can use a 2-hole lug if you want to, but it's not necessary. As long as your lug is rated correctly, you can just have 1 lug connected. Okay. The battery input. Now, this is extremely important. Positive and minus. So you should connect your battery positive, which should be a red cable, but don't trust the cable color. Okay. Always, when you are connecting up a battery to a system for the first time, obviously this one here should be black. Remember, we have a breaker up here. So you can connect these 2 cables without worrying as long as that breaker is open. But what you need to do is you need to get a multimeter, and you need to put your positive cable from your multimeter here, your black or negative cable from your multimeter here, and you need to check with that meter that the polarity is correct. If you connect this reverse polarity, and everybody will say, oh, we would never do a thing like that. You have no idea how many times people connect a battery to our system reverse polarity, don't check it, then they close the battery input breaker and they damage the system. Okay, and we're not going to come out and replace that under warranty. If you do that, and we'll know that you've done it, because there's some things in there to try and protect serious damage from happening, but we'll know that you've done it, and unfortunately we'll have to charge to come out and fix that. So don't do it, and therefore we won't have to come out and fix it for you. The next, so that is the AC input, that's the battery input. So now the AC output. So this is what you connect your load circuits to. Okay, so this is going to be your live or line output. and then you would connect your neutral here. Okay. And if you're running 3 wires out to the load and you're running a ground as well, that is where you would connect your ground cable. So these are for your load circuits. Okay. And then the final connection would be your bypass. Now, the bypass and the AC output share the neutral. So you would connect your line or live output to terminal 110, and then you would connect your neutral out on wire 15. And once again, if you're running 3 wires out to the bypass, then with a ground, then you would connect the ground there. So if you have your load ground connected there, you would connect your ground to your bypass on that second hole there. Okay, and obviously we give you the size of our holes and the hole spacing and all that kind of good stuff there as well. Now, I mentioned that we were going to talk about the grounded output connector, so we'll do that here. And this confuses a lot of people, because what you get is you get 2 bus bars shipped with the system. Now, obviously, we don't know if you've got a high resistance ground network, if you're putting this on a ship and there's no ground. We don't know what you're doing with your ground circuit. So we have to give you the ability to connect your system in many different ways. But the easiest thing to remember is this terminal is connected to the neutral. So basically, it's connected over to this neutral here inside the system. Okay. This terminal here, let me clear that out. This terminal here is connected to this ground terminal. Okay. And then this terminal is connected to the chassis of the UPS itself. So the metalwork inside the UPS is connected to that terminal there. So if you want to run an ungrounded output, in other words, which is going to be in most cases the way that you do that, you do want your ground to be connected to the cabinet. Okay, you want that as a bonding point. So you would usually just have this bus bar connected, because in truth, if you know anything about separately derived sources and UPS supply in general, and the way that you're only supposed to connect a neutral to ground at one point, and that is a point closest to the supplying power. In other words, closest to the transformer that is supplying power to the system. So therefore, for your bypass, there's going to be a transformer for your bypass. Actually, let me do it down here. There's going to be a transformer for your bypass, which then feeds in here and then up to your neutral. And then at the secondary of the bypass transformer, that is where you're going to have your ground connected. So if your ground is connected at the secondary of the bypass transformer, that means you do not want to connect another neutral to ground here, because then that's a secondary point and that will allow circulating currents. Okay, so 95% of cases, the only bus bar that's going to be connected is the ground to cabinet connection within your UPS. Okay. And then the last thing that was on that second page of the outline was the alarm relays. And basically it is saying alarm connection here, and it says reference sheet 2 of the inverter schematic for name tag arrangement. So basically there's a name tag on each of these connections, and then this is normally closed, normally open, common connection. So 3 connections for each tag. And depending on how many alarms you bought from us at the time that you purchased the UPS, will depend on how many alarm boards you have and how many connections you would have. And then we have the mimic diagram. And this is an exact replica of the front of your UPS. Okay. So once again, on this UPS, it's showing the AC input breaker. We have a float push button and an equalized push button. Okay. And you can see down here, the indicator color, R is red, G is green, and A is amber. So here we're saying that the float lamp is green and that the equalize is amber. There is the two voltmeter and ammeters that we talked about on the block diagram. We have a sensing circuit inside a system that basically it measures if the voltage is dropped below 127 volts for a 60 cell system. And if that voltage measured there goes below 127 volts, then this red alarm will come on saying the battery is supplying load, because in normal operation, the battery should not be supplying load. This one here can be a bit confusing. I'm not quite sure why we made that LED green, because the battery input breaker open is not normal, so it should not be green, in my opinion. But it is. So if you see this light on, then that's telling you that the battery input breaker is open. On the inverter, we have this in sync light, and it is green, and obviously that should be on all the time because the inverter has to synchronize itself to the bypass source. And then on the static switch circuit block, we have S201, which is the inverter to load push button. Once again, the light is green, and we have a bypass to load push button, and the light is amber. And on this UPS, they only bought 3 alarms as part of their alarm package, and that is bypass source failure, fan failure, and low DC voltage, and they are all 3 of them are red LEDs. So if they're on, that's telling you that you have a problem. But once again, this is an exact representation of the front panel of your UPS. So now we're actually going to go into the actual schematic for the microfarad UPS. And you can see here, once again, we've got the project number down here. And this this is page 1 of 1, because this is saying that this is the battery charger portion of the drawing, okay? And there's only one drawing for the battery charger portion. Is this the best way to do it? I personally would have liked the charger, inverter, and static switch drawings to be sheet 1 of 1, sheet 1 of 3. So charger, sheet 1 of 3, inverter, sheet 2 of 3, and static switch, sheet 3 of 3, or something like that. But remember, we do sell battery chargers individually, and we sell inverters individually. So that's why the drawing is labeled as sheet 1 of 1, because there is only one drawing for the charger. And I've circled this in the bottom left-hand corner. This is not always in the bottom left-hand corner, but it is describing what all the cable sizes are. So if you look here, it says here that if a cable is labeled A, then it is a number 18 cable. If it's an M, then it is a 2-aught cable, okay? And then also we have these symbols here: isolated, twisted pair. This is a tie point, and then this is just twisted, non-isolated twisted pair, okay? And also please remember, wires may be parallel to the larger power requirements. So if I go onto this page here, for example, you can see here, we see cable number 334, and then it says J. So the cable number is 334, but the J is saying it's a number 2 cable. I hope that's clear. Now, if this was a larger system, say this was a 50 kVA system, just for example, that may say 334JJ. So if we have JJ, that means there are 2 number 2 cables in parallel. And you can see here, this wire here, 338, it does not have a letter after it. So if we go back to our table, all unmarked cables will be 22 gauge. So if it doesn't have a letter after the wire number, then it is a 22 gauge cable. Okay. And that's listed on all of our drawings. So you can quite easily tell what size cable you're dealing with by looking at that. Oh, sorry, I went too fast. So let's go through the power flow of the system for the charger. So we have our three-phase coming in here. Once again, A phase, B phase, C phase. And you notice there is no neutral being ran here because this is a delta transformer. And a delta transformer does not need a neutral. Okay, so don't run a neutral to the UPS because there's nowhere to actually tie it to. You want 3-wire and ground to our UPS systems because all of our inputs are a delta transformer. Okay, and you can see that there is no physical connection between the primary side and the secondary side. So we have an isolation transformer here, and we go from delta to star. So we have our star or Y windings transformer on the secondary. So this transformer is giving us isolation, and in truth, it drops. It's a step-down transformer. So phase to phase is going to drop it down to around about 120 volts for a 60-cell system. Okay. And then that goes through these 3 fuses into our rectifier bridge. Okay. So here's our rectifier bridge here, and it's just actually quite simple. We have 3-phase going in the middle of each pair of SCRs. So this is an SCR, a silicon controlled rectifier. Okay. And you can see we're tied into the midpoint of here, the anode of this one and the cathode of this one, and the same for this one and the same for this one here. So we have 3 phases, A phase, B phase, C phase going in and then out. If you measure across here, we have DC. So it really is as simple as that. We have AC going into the SCRs and we have DC coming out of the SCRs. Obviously, we have this control board up here that's doing all the clever work. And on a microfarad system, the older systems, that is actually an analog board. So there's no processor on this charge control board. But that sends all the signals to the SCRs. If you look here, these cables 1, 2, and 3 are monitoring the secondary of this transformer because we have to know when to turn these SCRs on. So that's us looking at the sine wave that's coming in to our system, and we can phase our SCRs on based on this voltage going into the control board. So it's very important that the voltage is correct going into that control board. Out here we have our float equalized pots, and when I say out here, they're usually mounted on the inside of the system to the right hand side. They're not mounted on the charger control board. They're separate. They're usually 2 stainless steel potentiometer knobs. One is for float and one is for equalize. On this system here, there is a timer circuit. So this has an auto equalize function. If they lost power for a set time, whatever you set the timer for, then when power comes back on again, it will start the system in equalize mode for a certain length of time. And basically the float pot and the equalize pot send back the reference signal. This is a reference signal for the voltage. So this is where you set float to 135 and equalize to 140, usually, but check your battery manufacturer data sheet to make sure. Let me take a drink. I've been talking a lot. Hope I haven't numbed your head already on this week before Christmas. Okay, and then the firing signals for the SCR. So for us to tell the SCRs when to switch on, for these top SCRs, we use these channels here out of the control board. And then to prevent the drawing getting really messy, for these bottom SCRs, we reference the terminals here, 23 and 24. So that's that terminal there and that terminal there. This one here is 372 and 373. Sorry, 25 and 26. That's 25 and 26. It's cable number 372 and 373. And the same for that one there. So that's actually what sends a signal to the SCRs to turn them on. And that's what regulates the output of the charger. And then the final connection on that board is the feedback signal. So we are measuring the voltage feedback on these two terminals here. So this is the positive and this is the negative. There should be 135 volts in normal operation going back into these terminals here. And that's what tells the control board the feedback of the output of the system. If that goes down, then the control board says, okay, I need to send a signal to the SCRs to turn on earlier in the cycle and get more voltage to the output, and vice versa. Okay. We have our voltmeter here. The voltmeter is protected by a small fuse, just in case there's a fault in that meter. It doesn't put a short on the output of the system. The fuse will blow and the system will continue to operate as normal. And then down here we have an inductor. So that's a symbol for our inductor, or a choke, and that's part of the filtering circuit for the charger. It's basically like a transformer that just has one winding. Okay. And then across that transformer we have a suppressor. It's basically just an RC circuit, a resistor, and a capacitor across that inductor. Because if you know anything about electricity and electronics, if you stop current flowing through an inductor, there will be a back EMF, there will be a spike caused, and this snubber circuit basically gets rid of that spike. Okay. And then our positive and negative output here goes out to our battery and our inverter. And we'll see that on the next page. So this is the drawing for the inverter bridge for the microfarad system. Goodness me, 10:37 already. Woo, I need to speed up. So this is the inverter, and this is page 1 of 2 for the inverter. Okay, so there are 2 pages for the inverter, and we'll zoom in so you can see it. So you can see here is our rectifier battery charger, and there's the terminals coming out. That's a positive and that's a negative terminal coming out, and that's connected directly at the positive here and the negative here. Then here's our battery input breaker, and we would connect our battery out at this point here. Okay, so therefore our DC comes into the inverter this way, and you can see we have another choke or inductor in our system here, and we also have some DC capacitors. That smooths out the output from the charger even more, to make sure that the voltage going to the battery is nice and smooth and doesn't have any spikes on it. And then that then goes through this fuse here, which then goes to our inverter bridge. And if you follow this, so our positive, this is our positive cable, that goes in to the center of a transformer. This is a center tapped transformer. Okay. And it's quite simple. We have 2 transistors in our inverter bridge on a small 10 kVA system like this. So if we turn this transistor on, that will allow us to energize this portion of the transformer, because we have to get back to negative this portion here. So that would give us a negative going portion of the sine wave. And then if we then energize this one, we follow the positive all the way through, and that gives us positive with respect to this side of the transformer. That gives us a positive pulse on the second half. Okay, so really the output of this system will be a square wave that looks like that. Sorry, not on that side, that's on that side. Okay, but then this is a ferroresonant transformer, and it has a capacitor bank in here. Okay, and what that transformer does is it regulates the output and it converts it into a sine wave. So we have a square wave on the primary, but on the secondary we're going to have a nice sine wave coming out here. And we have E1, which is a frequency meter. M1, M stands for motor, so that's M1, so that's actually a fan. I know we probably should use F, but we use F for fuses. So an M is a motor for a fan, and then V1 is a voltmeter on the output of the inverter. Okay. And then here's our inverter static switch control board. And that's what sends the signals to the snubber board, which then feeds the gate emitter signal to the IGBTs, the transistor. Things to point out on the inverter section. So we do have this B1 aux contact here. There is no inverter start push button on our microfarad inverters. Basically, when you close this DC input breaker here, there is an auxiliary contact here that closes, and that sends a signal to the control board and tells the inverter to start. So that is how we start the inverter on our microfarad systems, by closing the battery input breaker. Okay, there's no other way to start the UPS. You have to close this breaker and it sends a signal on these terminals to start the inverter. We also have a monitoring circuit. So we're monitoring the DC here. So we should have 135 volts there in normal operation. If that drops down to 105 volts, which is our low level voltage for the battery, the control board says, okay, I don't want to over discharge this battery any further because it could cause irreparable damage to the battery. So what it does is it sends a signal out to K4 relay. Okay, you can see it up the top here. We send a signal out, we energize K4, that closes this contact here. And if you look, this is a positive DC, and this here is the negative, and our coil for the battery input breaker here is connected in series with that contact. So when K4 energizes, B1 coil energizes, and that trips this breaker here and disconnects the battery from the system. We do have a circuit inside the inverter that says, okay, we will, let me just actually say, this is the inverter static switch, and this is the bypass static switch. When we do trip this breaker at the 105 volts level, we do send a signal and turn on the bypass static switch a few milliseconds before we trip that breaker to make sure we transfer to bypass before that battery input breaker is tripped. Okay. So once again, nice, beautiful sine wave coming out here. Then that goes through fuse F204 into our inverter static switch. And as I said earlier, a static switch is actually just two SCRs back to back. And all we have to do is send a continuous signal to the gates of these SCRs, and it will allow that sine wave to pass through. Okay? As long as we're sending a signal to these SCRs, the sine wave will pass through. And we're not sending signal to the bypass SCR. So yes, we will have power available at this point here, but it's as if this switch is off. Okay? Remember, there's no moving parts, static switch. Okay? And then that goes out. Once again, our sine wave goes out, and we have this T202, which is a CT monitoring the current out of the system, and it reports back, if you see here, to this control board here, and it's monitoring the output current of the system. And if the output current gets too high, and if the bypass is available, it will tell the system to transfer to bypass, clear the fault, because we don't want to clear faults with the inverter if we have bypass available. And then our load circuits are connected here. The only other thing that I'll mention is here's our bypass coming in here, 120 volts, single phase. And then here is our bypass AC input breaker. And then you see here that we have a contactor, K1, connected across the input to the system. So as soon as you close this bypass source AC input breaker, this coil should energize. And that pulls in the contacts related to this coil here. So basically, it's allowing the current or the voltage to get to the bypass static switch. This is our UL backfeed protection. And basically what it does is, let's say, remember the inverter should be flowing through here out through this static switch in normal operation. Okay, if you're going to do work, basically what UL says is if you're going to do work on here and you want to de-energize this back at your MCC, UL says you have to have something that if we have a short circuit here, so that becomes connected to that through a short circuit, then we need a circuit that says, okay, if somebody has deliberately switched off the bypass here, that de-energizes this coil here and opens up these contacts. And therefore, we can't backfeed the circuit this way when somebody has deliberately switched off the bypass AC input breaker. And that means if somebody is working back on the MCC, we don't backfeed power onto that system if we have a failure in this static switch. So it's a UL safety mechanism to prevent. It's kind of like if you had a generator on your house, you have to have the protection in place so you don't backfeed onto the pole and kill a lineman, basically, if he goes there to fix it. And then page 2 of the inverter diagram tells us about the control boards, and we'll just zoom in on this. X5 is a display alarm controller, and you've got all these LEDs on the board, and it tells you what each of the LED is and what it shows you. So all of these LEDs, the power supply LED should be lit. It's saying this one here should be okay and flashing. This is telling you if there's a ground fault positive, ground fault negative, so they should not be lit in normal operation. These are communication failure alarms with this relay interface board. So if there was a problem with the communications here between this board and this board here, it would give you a red LED saying relay communication fault. And this one here is just a red fault light to tell you if there's anything wrong with this board whatsoever. And then this X5 indicator alarm board, that's basically what deals with the outside world. So the inverter push buttons and all that kind of stuff. That's how you put the system in float, equalize, inverter to load, bypass to load. So that does all the interactions and tells this board here what to do. Okay, sorry if I'm going fast, but needs must, unfortunately. And then this is where it gets complicated. You know, I mentioned a static switch. Now we're going to talk about a remote manual bypass switch. And please bear in mind that we sell RMBSs as a separate entity to our UPS. Yes, you can buy a UPS with an RMBS and you will get sent the whole package together. But you can just buy an RMBS. You can buy a UPS without an RMBS. We don't recommend it, but you can. So the drawing for an RMBS is usually always separate to the UPS drawing itself. So as you can see here, it says sheet 1 of 1, and this is the outline for a remote manual bypass switch. And we're going to zoom in on each portion here. Okay. And basically what an RMBS does is it allows us to isolate a UPS for maintenance or replacement and still keep your load circuits powered. But the most confusing thing is if you get shipped an RMBS and a UPS separately, how do you connect them together? And I understand the confusion, but it's actually quite simple. And the confusion is usually caused by the wording at these points here. So we have bypass source AC input, bypass source AC output, normal source AC input, and the AC output. Okay. We're going to see in a few slides' time that it's actually a lot more simple than you think. But this is the load. Okay. And this is the bypass from your MCC or your bypass transformer. Okay. So that's your external world. So basically, your bypass comes this way here, and then that goes to the UPS and supplies the bypass to the UPS static switch. Okay. And remember that static switch is usually off. And then the output of the inverter static switch comes back this way here and feeds power to the load. And that's why in normal operation, it's shown here that this contact is open, this contact is closed. So bypass goes to the UPS this way, and the output from the UPS gets connected on this one here. Okay. UPS has 3-position rotary manual handle on the front of it. There is no automatic function in this whatsoever. This is a rotary switch. And then we have this mimic panel or front LED panel, and it shows you what's on the front. Once again, green, red, amber. So you should only have green lights. So you say normal source to load, normal source available, bypass source available, and in sync. That is the alarms that should be on your RMBS at all times. Okay. And here is a schematic diagram. It's exactly the same as this one here, but it's just in more detail. And I've blown it up so you can see. Now, so here's the rotary switch, and it says normal operation. Any contact with the number 1 written next to it is going to be closed in position 2. Any contact with the number 2 connected to it is going to be closed. And in position 3, any contact with the number 3 is going to be closed. So let's go through this drawing. Position 1. Okay. This contact here has a 1 next to it. So that is going to be closed when we are in the normal operation. This one here has a number 1 next to it. So that is going to be closed. So remember I said this is from your MCC. Bypass supply is going to go that way into your UPS. And then your UPS is going to choose the inverter source and go out this way through that contact there out to our load circuits. This does not have a number 1 next to it, so that will remain open. Now, when we go to position 2, you can see up here that this has a position 1 and a position 2. So this remains closed, okay? But this one here, it doesn't have a number 2 next to it. So this opens, but it is a make before break switch, and this has a number 2 on it as well. So what happens is this actually closes before this one opens. And what happens, what you're supposed to do is your bypass is going to be coming out to your static switch in here. So your static switch, okay? And it's normally choosing the inverter output. Before you roll this switch between position 1 to position 2 or position 2 to position 1, you should always put the static switch to bypass, okay? So our bypass is going to be coming out through here now. And what that does is that ensures that this side, which is connected to the bypass directly here, is bypass. And this side here is bypass. So when we roll this switch to position 2, we are paralleling bypass and bypass together before this one here opens. So that's what allows us to have the make before break arrangement. So your load circuits will stay on. They'll continue to be powered when you roll that switch from position 1 over to position 2. So that's kind of complicated. So what I've done is I picked out a drawing where they've actually shown that connection for you. So here is a UPS, charger, inverter, static switch. Okay, and then here is our MBS, sorry. Okay, so I'm going to zoom in on it for you. And as you can see, this is coming from your MCC. And then we actually supplied a bypass transformer for the customer here. So the bypass comes in here, and then it goes out into the bypass for the UPS. But the output of the UPS goes in here, out through this contact here, and out to the load. But why I wanted to, the real thing that I wanted to show you here is, because we're the manufacturer, we know what the cable numbers are going to be. So we always label our cable numbers so you can easily match them. This is why 110 in the RMBS, or terminal 110 in the RMBS. This is terminal 110 in the UPS. As long as you match those terminals, you're good. Terminal 199 in the UPS, terminal 199 in the RMBS. Just connect those together and you will be good. Okay, same with the 15s, connect them all to the neutral bars. So this side here is the most confusing thing for most people, but if you follow the wiring in both the UPS and the bypass switch, you can't go wrong. Okay. Well, it looks like we're going to overrun today, so it is what it is, because we've still got to go over the DPP. So this is our new system, our newest system. It's been out since 2003. This is one that we sell most of out into the world at this time. So once again, this is our general arrangement, just exactly the same as the previous UPS. We show you the front of the system, the dimensions, the top view, and the view from the bottom, and the view from the side. And our block at the bottom here shows you the serial number and everything as we discussed. Okay. This system here, because it's a digital system, we don't have any analog meters on here, although you can order them separately if that's what you want to do as an option. And then our serial number is down here. And once again, we're listing all of the breakers. So that's CB5, CB3, CB2, and CB1. And then also the inverter enable on and off switch, which is this switch here. And then this is the page that shows you the alarm connections, your block diagram, and your startup and shutdown procedure. Always follow the startup and shutdown procedure for your UPS. That was designed specifically for your UPS. It was tested in the factory. It was tested at FAT. And if we perform the startup, that is the procedure that we use to start it up and shut it down. So it has been tested. It works. If you follow this procedure, you will be able to shut the system down and maintain your load circuits. Okay? Always follow this procedure and don't skip any steps. So once again, this is a block diagram, and it's exactly the same block diagram as microfarad. So I'm not going to go over it. Once again, it lists all your inputs, what the maximum current that you're going to see, so you can size your cables. It's all the information is there for you to do that. And there's a startup and shutdown procedure. I'm not going to go over each step. That's not what this is about. It's just to show you that this is specific to your UPS. They do change for customers. Some customers have different breakers, have different things. So this is specific to your UPS, and it will be specific to your UPS in your manual. And this diagram shows you where your connections should be made. Okay, I think I zoom in. So we've got our positive and negative cables going on here. So you can't see it very well, but this is actually a tab, a bus bar tab coming from the back of the breaker itself. That is where you connect your negative cable from the battery, and that is where you connect your positive cable from the battery. Okay. Same with your AC input terminals, A phase, B phase, C phase on the tabs on the back of the AC input breaker. And then for the loads, your load is connected to these terminals down here. So the AC output goes here, 15 is your neutral. There's your system ground. So it gives you all the customer connections so you can tell your guys where to connect them. And then we have our Mimic. Okay, this is now a touch screen. So you do all your interaction through the touch screen, and there are some push buttons on this keypad here as well. And it tells you down here what each of the button does. That is how you connect to our system using a computer and download alarm logs and details about the system. And this is the inverter on-off switch. If you remember previously, I said for the microfarad, it doesn't have an on-off switch, but for the DPP, we do have an on-off switch. And you can see here we have, on this system, we have 3 LEDs, a UPS normal, a UPS trouble, and an in sync. In truth, you can, I think it's a row of 6, it could be more. Depending on what your design engineer bought, you can have many more LEDs on the front of your system. So once again, this is specific to the system that you bought using that serial number. And this describes all of the alarms that will alarm on your Mimic screen and will report to the DCS on the common alarm. So if you got an alarm on the system, if we go back, if we got this UPS trouble alarm, what this is saying is it must be one of these alarms that caused that trouble alarm. And these ones here, obviously, as well. They are all the options that have been enabled on this particular UPS. And that's it zoomed in so you can read them. Okay. Once again, here's our rectifier, and once again it goes in through a circuit breaker and then into a delta transformer. Okay, this is a digital board. So we have, this is our communications board with fiber optics coming out here. So that's what connects to the brains of the system. And so this is actually a digital charger, but the principle is exactly the same. We've got our AC going in here to our SCRs. So AC on this side, and then we've got DC coming out on this bus bar here. Okay, we're still using SCRs here. This is where the board gets its 3-phase input to know when to turn on the SCRs, well, the reference signal. We have this TH1, that is a thermocouple that is attached to the heatsink that these SCRs are connected to, looking to see if there's something wrong and the SCRs are getting too hot. If that closes, and that closes at 90 degrees C, not F, 90 degrees C, which is bloody hot, then it will shut down the rectifier to protect itself. And then on this system here, this is actually an option. We have indicators on these fuses. And if one of these fuses blows, this will close and it tells the system that one of those fuses has blown. Then we have our DC capacitor here that filters out along with this choke here. So it's pretty much exactly the same as the previous microfarad drawing for the charger. And that's it zoomed in. I should have done it on the zoomed in drawing, shouldn't I? But I'm rushing myself. And then this is the inverter drawing, okay? So we've got our positive at the top there and our negative coming in. And then it goes into our inverter H bridge. And basically what we do is we turn the IGBTs on, which is an insulated gate pipe bipolar transistor. So it's our power switch of choice, and the power flow will be through that transistor out to our transformer here, and then the negative will return down through there and out back down to our negative. So that will give us our negative going, because remember this is more positive than that. That gives us a negative pulse of PWM, because this is a PWM machine, which is pulse width modulation. And then when we switch this IGBT set on, then if you follow the positive through, and I can't draw to the top there because there's something in my way, but basically power comes down here through that, and then goes back up this transformer to here. So this becomes positive there, and then the negative goes down through this IGBT back that way here. So that's negative. So this way we get the negative going pulses. So if you took an oscilloscope and you went on this transformer here, what you would actually see, and this is a very crude, rudimentary version of what it is, because it's actually at 8 kilohertz we do this, it would look like that. There's your zero line there, okay? But coming out of here, because of the inductance in the transformer and the capacitor, we will have beautiful AC coming out here to your load circuits that way there. Remember I said that we trip the battery at 105 volts. This is what this circuit here is doing on this control board, and it makes this relay 1 close and shunt trips the battery input breaker there. Very similar to the micro SE UPS. This is an indicator only on the DC input breaker. It tells us whether the battery input breaker is closed or not. Okay. This is the inverter enable switch, switch 2, which is that rotary switch on the front of the UPS that turns the inverter on and off. And TH2 is, once again, it's a thermocouple that's attached to the bridge that these IGBTs are mounted to. And if that goes above 90 degrees C, then that thermostat closes and it will shut down the inverter. Actually, I think it transfers to bypass. I'd have to check on that. I can't remember on the DPP. But it definitely takes the load off of the inverter so it can cool down. Once again, here's our fiber optic cables. Here's where our fan sensing is connected. Our fans have tachometers in them. They are monitoring the speed of the fans. And if the bearings are starting to go, then the fan will slow down. And this is what monitors the fan tachometer here. What else do we have on this board here that's of interest to you? Nothing really. It just tells you what the LEDs on the board are there. Okay. And then this drawing is the static switch. Okay, so it tells you which sheet it comes from, sheet 2. I know, obviously, this cable here is the bypass input because we have our bypass input breaker here. So therefore I know that this is the bypass static switch, and I know that this is the inverter static switch. So in normal operation, power flow is down out here and out to our load circuits. And only if the inverter fails or something happens does this turn on and we have bypass flowing in out to our load directly. Okay. This shows you how all of our boards are connected together, and here it is zoomed in. So PCB 13 is a display controller. That is the PCB that's mounted on the back of the door that's connected to the touchscreen display. This is the brains of the operation. It tells the system what to do, okay? And we connect through the fiber optic cables on here to tell the system what to do. This goes to the charger board and this goes to the inverter static switch board, okay? And we have our relay board connected to that system as well. So that is all the boards in the system. We mentioned the charger and the inverter static switchboard earlier, and now PCB 13, that is the brains of the system. And what I wanted to do with that, this is the relay board here. I've turned it 90 degrees so you can see it better on this next page here. We try and make it as easy as possible for you, okay? So we're saying for the common alarm, under normal operation, the relay is energized, okay? So we're saying if there is no alarm, the common alarm is energized. So unfortunately, relays and alarm contacts get so many people confused. And I understand why. I sometimes get confused myself, but we're trying to make it easy here. So what we're saying is, if everything is healthy, this common alarm will be energized. Now, most plants will connect their alarm signals back to their DCS system in what's called a fail-safe mode of operation. What they're looking for back, so if we connect our common, so back to your DCS system, is we want an open contact for a fault. And the reason we have that is if somebody comes along and cuts that cable, this contact to the DCS goes open, and you will get an alarm if somebody cuts those cables. So we want a normally open alarm to describe a failure. So if under normal operation the relay is energized, we would then connect to the normally open and the common alarm, because when this energizes, that contact is going to be closed. So it's going to be closed in normal operation. So the DCS sees that as healthy. And it's only when this relay de-energizes for a fault, that contact here, let me erase that. That contact there will open, and the DCS will give an alarm. Okay. And I'm going to get to your other question later, Charles. I just saw your question there. What communication protocol does the brain use? We use fiber optic cables. I'm not sure what the language is, but you cannot connect, you cannot control the system with your control system. Okay. You can connect, if you want to connect to our brain, then we do offer Modbus, RS-232, basically any communication package that you can think of, you can connect to our control board with, but you can't actually control the operation of the system. You can only monitor through those connections, if that makes any sense. So it can be Modbus, RS-485, just all of the standard communication packages will connect to our system if you have that option. Okay. And then the last page for this, I think, is the power supplies. Do I go into it in depth? Yep, there it is there. So we use 3 power supplies for the DPP to supply our logic supplies for all of the control boards in this system. So we have one is from the battery. Okay. One is from the AC input, which is the AC input transformer, the 3-phase 480 that gets stepped down on an auxiliary winding on the transformer. And the third one is from the bypass supply. Okay. They all go onto this power supply distribution board. And 2 of these can fail, and the system will run. As long as you have one of these, either that one, or this one, the system will operate as normal. Okay, so we have triple redundancy built into our power supplies. and then all the power supplies go out to our boards using these terminals. Yeah. Okay. Oh, cool. So sorry I rushed at the end there. I always tend to talk a little bit too much, and hopefully the information that I've given you so far has been good. So now is your opportunity to ask questions in the chat. I've already got one from Charles. So if I wanted to put a transfer switch with a generator, we would just put a 480 volt on the input with no neutral and ground. I'm trying to figure out what you're actually saying there, Charles. So if I wanted to put a transfer switch with a generator, we would just put a 480 volt on the input. If you're talking about not related to a UPS and you are using an emergency generator through an automatic transfer switch, it depends what your load circuits are looking for. If your load circuits are going to need a neutral, then you should obviously run a neutral. It's what you do with the neutral to ground connection. The output of the generator is a separately derived source. So that generator should be creating a neutral. So that neutral should then be tied to ground at the generator itself. Whether you run a neutral or not to your load circuits is completely dependent on whether the load circuits need that. In truth, the output of that generator is usually going to go through transformer in many applications. So you would then choose what to do with the neutrals after that. But a UPS or anything that creates a new power supply compared to what comes from the grid is classed as a separately derived source. Okay, so that means whenever you create a separately derived source, you have to bond your neutral to ground as close to that separately derived source as possible. Hopefully that has not confused you too much, Charles, but that's what I've been trying to say. So Joshua has asked, is Modbus TCP supported? Yes, Joshua, Modbus TCP is supported. So thank you for that question. So while I look to see if any other questions are coming in, I appreciate your time. Sorry I ran over, especially so close to lunchtime in many places. I hope you enjoyed the presentation. I hope you learned something from the presentation, even if it's just one or two things. It's good to learn at least one or two new things every time you go through one of our webinars. Remember, you can go back. If I confused you because I was going too fast, Taylor has just put in the link there to our YouTube channel there. You can go back tomorrow and you can review this video and go to the parts, listen to me once or twice, because it is difficult to listen to my accent for an hour and a half. So you can go back and listen to it again and see if you can clarify what you wanted. Also, Taylor's going to put in the chat bar how to contact us through our web portal. And if you go back and you look at the presentation and you see something and you just couldn't figure it out in your head, and you would like us to try and help you with that, send an email using that contact form or using the email address that Taylor's put in the chat bar there. Send an email to us and we will try and reply and clarify the question that you have been asking. And you can give us a call as well. Okay. So it looks like that is going to be all the questions we are going to get today. So once again, thank you for your time. We really appreciate you coming along and spending your morning, afternoon, or evening with us. We try and give you the best content that we can. Marketing will send you a survey to all of the people who came to this presentation. one of the questions that they ask is, please give us a subject for a webinar for the future presentations. And we really like to hear what you want us to discuss on these webinars, because obviously we live and breathe UPSs every day. So we're pretty much experts. So we know all of this. We want to know what you want to know so we can help you understand your systems in the field even more. So if you have any suggestions whatsoever for a webinar in the future, please send it to them. I read every single one of them, and I always implement it if I possibly can. So until next time, have a wonderful holiday season, whether you celebrate Christmas or not. Have a fantastic holiday season. Enjoy the new year. I hope it brings you everything that you want. And we will speak to you again in January sometime with our next webinar. Look for your emails to see what the subject is going to be. But once again, thanks for attending, and we'll talk to you soon. Bye-bye.